Thank you. So I was asked to talk today about information extraction from social media. I guess the topic is relevant to Yandex, and that's why we decided to focus on this one. So this is a work with my students and my postdoc, Christina, Arya, and Ted. And so this topic is of social media is so close to our heart that even when we were going to Moscow, to this trip to Moscow, we had to make a choice of a hotel. And it was a non-trivial choice. So first, my assistant found us this hotel in Ingradskaya, and we were supposed to stay there. And the reviews looked sort of okay. The first one were great, so it sounded amazing. But then we continued looking, and then we found all this terrible, terrible review, which is a clear no-go for the hotel, so we don't stay in Leningradskaya. But this is just one example. So we see a lot of this user-generated data on Twitter, Facebook, whatever, your favorite blogs, or plenty of it. So people today make a lot of their decisions based on this data, and there are a lot of studies, like especially in social sciences, how much we today rely on the review data to make various purchases and so on. And we can't read it all, even though I did read all the reviews for Leningradskaya before we decided not to go there. So the idea here is that natural language processing can help. And luckily for us, because you look at this data on the reviews, and they actually look pretty bad, correct? Because they're not written in formal English, they're not edited or informal Russian. So you say, how, for God's sake, I can take sort of some proper linguistic approach and analyze it? So the good news is that people in natural language processing discovered many years ago you don't really need to have a very complex linguistic analysis. You can just build a very simple statistical model to make your prediction task, and it will work. So here you can see, let's say we have a very simple task of predicting the topic of the document, like it's some financial document and some weather-related report. You can just see that looking at the word distribution, it's enough for you to make this prediction. So you can use some very standard classifier to make this prediction. Even if you look at the task which is sort of more complex, like semantic analysis, you can say, let's say I want to write about every word, what kind of role it has. So you have a sentence, the earthquake injured 3 people, and semantic roles that you may want to have can be event, and number of dead people. So you would have just 3 classes: none, the type of event, and the number of casualties. And in this case, you can use standard sequence label prediction model to identify this role. It can be HMM or CRF or whatever you like. And those things work quite well. So currently we can look at natural language processing and think about it sort of like this kind of dialogue, that we don't really have to understand the whole message. It's enough for us to identify just few words in the message. And long time ago, one of my very favorite people in our field, Fred Jelinek, said every time I fire a linguist, the performance of the speech recognizer goes up. He was the person who built the first hidden Markov model and applied them successfully to speech recognition. Now I should say that Fred Jelinek, who died last year, actually towards the end of his life had a very different understanding. He was all pro-semantic and pro-linguistics. So what I will try to do today in the talk is to say that if we really want to be able to process more complex text, more colloquial text that Wall Street journals that we typically use for our analysis, we may need to use more linguistics. And what I mean here is that rather than just using a standard bag of word approach, I will slightly embellish my bag. And what I will try to do, I will try to model some structure of the documents or connection between documents, and I will show you that for tasks, for several tasks, it actually makes a big difference, especially for social media analysis. And another goal that I will try to achieve is to show how you can take a lot of raw data that is available on the web, which is unannotated data, and add it to your supervised model and to get better predictions. So I will show you just few different applications. There will be no surprising techniques. It would sort of standard graphical models, which will model some linguistic connection. So the first system that I want to show you, it's actually available on the web. So after the talk, you can try it. I can show you it's alive and running, hopefully it dies. So you can just type the name of the restaurant, whatever you like, and there is one here. I mean, the restaurants are all, it's actually in the US. Before I came here, I tried to collect restaurants from Moscow, but apparently most of the reviews were about Moscow, which is somewhere in the United States, not in Russia. So I didn't find just a large body of reviews, but I don't think it's, it has any connotation to the country it should work. Okay, so what we ideally want to do here, let me just show you what the system does. The system takes a lot of reviews that are written about a particular restaurant, and then it predicts, it sort of selects all these sort of short summary phrases which tell you about the good and bad qualities of this restaurant. And you can see that it does it in the category of food, ambience, and service, and overall prediction. So we can have three, whatever, the much talk about vegetarian menu, which was all yummy, and a variety of others. So you can think about this task as just simple summarization by extraction. You want to take the body of all these reviews and to identify phrases which will be highly informative for this particular venue. I will use in this case a supervised learning, in the sense that it will be supervised because you will ask humans to give you some snippets. You will have a body of text, and then some people would go and annotate the phrases in this text and mark them whether they are important or not. And we would want maybe to separate them into different categories, food, service, and so on. Now you can see that whenever we are doing this kind of extraction, the content is actually crucial. You cannot just look maybe at a sentence alone and say, and extract the phrase, because if somebody said loved, you don't know what he meant by love. Either he loved the whole meal, or maybe he loved a particular dish. So whenever we have some phrase, we need to look broader than the very local context whenever we are making the prediction. Okay, so you see where I am sort of going with it, that what I would want to do is to combine two models. One would be standard sequence labeling prediction, where you go over every word and predict whether it is relevant or irrelevant, or whether it is a food description snippet or something else description snippet. But in addition to it, I would want somewhere to have a content topic model which tells me whenever I'm making my local prediction, what kind of topic I'm discussing using these words. So for instance here, I want to know that when the word dazzle here is used, it refers to the blue eyes of the waiter, and doesn't necessarily mean that I should apply this word in the description of the food in that restaurant. So we may want, given this black piece of text, to sort of identify different colors, to identify the document structure. Now, there are lots and lots of models in natural language processing that allow you to talk about the global structure of the document. So this word, one of them that I've heard many of you have used is topic models. There are also more sophisticated linguistic models like rhetorical structure, which sort of try, given some predefined set of relations, to build a tree of the text. So those are good. Now, if you look at the analysis application, there are plenty of models that can just take a text and assign roles to the words in the documents. The problem, however, is that the structures that you may want can be very much defined by your task. Let's say if what I want to do is to do information extraction to identify favorite dishes or something like this, I really need maybe to have a very elaborate structure. If I want to separate food and ambience and all those things. If I just want to do sentiment analysis, predict whether the review is positive or negative, my structure should tell me which sentences are objective sentences and which are subjective. So, and the structure will be driven by your applications. That's what you would want to have. So what we will have, we will start with a standard sequence labeling approach for prediction of the labels. So in this case, you have some words, the words of your document, and then the labels will tell you whether it is food, service, atmosphere, or nothing. Okay? And this model I'm sure many of you have seen. So what we will do next, we will augment these models with this hidden layer of content labels, which actually would correspond to the broader topic of the segment in which this particular extraction happens. So you can think about it that you have just an HMM over topics, but rather than just spitting out the words, it will be spitting out the words in the corresponding labels. That's the whole idea. And what we will do here, we will jointly learn this, our extraction tasks and the topics in one single model, as you probably guessed. And furthermore, I will demonstrate that this model you can very easily add unlabeled data. So let's just see how, to be very concrete, what we're doing here. So you're looking at joint of topic, words, and your labels, and you just factorize this probability into two. One which would sort of look at the topics, you see transition between topics, and the part which will generate the words from the topics. And then there will be another model which generates the label condition on the word and the topic. And pretty much, let me show these slides. So what will happen here is whenever you are making your prediction about the label, you would be able to look at the words. That's what you typically do in like CRF. In addition to it, you can also condition on the topic. So you are not making decisions just based on your very local evidence, but you can take a more global evidence into account by combining these two structures, one which just does content model and another one which does labeling. So that's the model itself. So now you can look at it's a very standard objective. You're trying to learn the parameters for topic and the task parameters, and here is your hidden variable over the topics. And it turns out that it's very easy to formulate EM in this model. During E step, you can just do standard forward backward, and during M step, you're going to do either like standard, count normalization or weighted conditional objective, likelihood objective. So this model can be done with EM. What is actually even nicer that now you can look at the objective and add to it the unannotated data. So this is our standard supervised objective, where you assume that you are given both the words and the labels during training. The next thing that we're going to be doing, we're going to be saying, I now want somehow to add unannotated data. So what is the most logical place to add such an annotated data? The most logical place to add annotated data is when you are learning the topic models, correct? So we can just use this extra data whenever we are predicting these topics over this component. And again, the same EM can be easily augmented to work with the same supervised objective. So the data set that we use for this task is Amazon reviews and Yelp restaurant reviews. So the system that is available online is about a restaurant. Now, as you can see, training is very small, and testing is sort of, again, 48 reviews. We have, as in label data, 33,000 reviews. Now I'm afraid to tell you, because I don't remember the number, but we have, I think, hundreds of thousands of restaurants in our database that is, that is available online and people are using it. So let me start by the information extraction task. So here is the task that I started with. You're given, all your different reviews for the restaurants, and you have all these different labels, and you try to color the text based on the label. Is the task clear? There will be three baseline systems that we are going to be using to evaluate. So one is you just use your favorite sequence labeling model. In this case, we use CRF. Then you can do the following. You can just learn your topic models separately and then feed them as a features to CRF. So you're sort of separating the two processes. It's nice because it's very simple. And the third one is our model which combines these two together. So here you can see the results for Amazon and for Yelp. So for Yelp, the results are, they're all not in 100s, but for people it is actually not bad. They're still using the system. What we clearly see across these cases that adding topical structure definitely helps, and in both cases, learning jointly does make a difference. Now, what I will do next, I will show you the slide about the impact of unlabeled data. So here on the Amazon corpus, what we read, we fix the amount of labeled data and start throwing in an unlabeled data. So here you estimate, what I mean 0 here, is that you don't have any unlabeled data, and you using your very small supervised data to estimate the topic. So it does 41, then you add 6,000, you get 47.3. You can see here that the difference is not great. I mean, you get some gain, but it's not very significant gain. Another task that people in the NLP community love dearly is a task of multi-aspect sentiment ranking. So you're given the review and you want to predict how many stars goes to this review. So in this case, we use a data set which has sentiment annotated from 1 to 10. So that's what you're trying to build. It's slightly different EM optimization. You can see details in the paper, but the spirit is exactly the same. So this is the L2 arrow, where the lower the number, the better you are. And you can see here that with joint model you get to 265, while 2 others actually do significantly worse. Now this was an interesting number. For some domains, we had, for this Amazon domain, we actually had golden annotated data. Those are standard reviews where you have written something like, this is a part about product, I don't know, whatever, price, and all these different subparts, where you already know the label as human predicted label. So you know exactly the topic. You don't need to infer the topic. It's given and it's true. And you can see that the difference between the model-induced topics and the golden data is not very large. So it actually does pretty reasonable job in predicting those topics. Okay? So this was the first part of my talk. So the paper is here. The code is available. You can play with it, and the system is available. Next part of my talk, we should have continued with a discussion of review summarization. And here it's coming back to our example of this Leningradsky hotel. You have many, many, many reviews. So it's not actually enough to just extract the summary from one review. And they sort of didn't tell you the full truth. How did I generate the review for Oleana? Because if I just generate from each one of the restaurants, I would have a lot of repeated things, correct? So we don't want to read this very long, repetitive list. So you can see here, this is a restaurant, another restaurant which is quite close to MIT, called the Hungry Mother. You can see there's 2 separate people, so they sort of each one contributed something new, that the oysters were very good, gnocchi was outstanding, whatever. But you can see that they agreed on the fact that grids are spectacular, but they had a different opinion about this catfish dish. Correct? So we somehow want to look at these reviews and aggregate them. We don't want to just present this big unstructured list. And if you go to many websites with products, you would see that almost every website provides you data in aggregate. So for Amazon, it would be just the summary of the ranks. But the summary of the ranks is not sufficient, because maybe overall judgment is okay. I mean, they found very good. What I really want to know is what are the points on which most of them agreed. And that's what we are trying to do, is to provide more informative aggregation of this data. Okay? Some time ago, we looked at the problem which is sort of related. It's called multi-aspect classification. It's when you say, okay, I know for many products what are the aspects that I care about. So for restaurants, it could be food and service and so on. So maybe I can sort of jointly train the classifier which predict the number of stars for each aspect. So it's simple. You just can link this classifier prediction together and do some fun stuff, because they're obviously correlated, and it would be a nice model. However, there is one serious restriction assumption there, which is that you know ahead of time what is a granularity, correct? That you just decide ahead of time which categories do you want to have. And many times you want something much more refined. So if you're talking about Japanese restaurant, you want actually to know maybe about sushi in particular and other things, rather than lumping it all together into food. And the type of aggregations that I would want to have is something like, tell me the best dish. What is it everybody loved? Or what all the people dislike, or which aspect of the restaurant people disagree with. And what I would want to do here is to be able to sort of dynamically predict both the relevant aspects for each restaurant and also to predict user sentiment for each aspect. So given the sets of reviews, for instance, for Japanese restaurants, you may want somehow to induce that there are subtopics like sushi, sake, and dessert, and for bakery, you care about cookies, cakes, and pies. You don't want to just lump them into food. You really want to have a very factorized description of the content. Okay? And now if you have such factorization for the different products, you can say what are the things that we liked about, that we all agreed, the consensus ones, and also the ones where people disagree, and you can see they always disagree on something. Okay, so again, as an input to this model, we will take the output of the previous model where we just extracted all these possible snippets. They would be segmented by the restaurant, so you will have bag of snippet for each restaurant. There will be no additional information. And what I would want to produce is relevant aspects for each restaurant. So I would assume that I will predict something different for Japanese restaurants than for pizzeria. I want an aspect label for each snippet and sentiment label. So you're going to get, lumped together all the opinion about burritos and all the opinion about salsa separated. Does it make sense? Okay. So the first, most obvious thought that comes to our mind is, why do you need to bother and do something fancy? You can just run simple clustering algorithm. You already have the snippet. You can see in this example that all the snippets that come to salsa, they all have the word salsa, and there will be all those that talk about burrito would have obviously burrito in them, hopefully. Just run your favorite clustering algorithm and you're going to get something reasonable. The truth is it's not actually bad, but many times it got screwed up because whenever it clusters, it lumps together as evidence sort of aspect word, which is like burrito or wine, with the words which are sentiment. So you can see that this is a bad cluster because it talks about very different dishes, but they all have the word best. So you want to make sure that the sentiment words are not the one that are driving your clusters, that the clusters are driven by some aspect words. And the solutions, so the models I will show you now, jointly models aspect and sentiment, and the way that you can distinguish, let me actually ask you guys, so how would you distinguish words automatically that are sentiment words from the words which are aspect words? What intuition would you build in your model?
To factorize into 2 dimensions.
So 2 dimensions, but what's unique about one? What is a characteristic of one class which it does not carry out for another one?
So it's the same.
So you can write the list of like sort of sentiment words, but what is another property of that group?
Sentiment words are more or less the same over
Exactly. So the sentiment words would be carried on across the whole corpus. You would say fresh and delicious or nasty. They all would be carried across the restaurants, but the different aspect words would be specific to the restaurants. So that's pretty much the idea behind that graphical model. So this is a model overview. Now I should be very upfront with you. The model sort of doesn't really look very beautiful and compact because it tries to do many things at once, but this is like the big overview, and then I would tell you different parts of the model. But that's what if something to be remembered from this part, it's this slide. So each snippet has an aspect and a sentiment, and each word will be drawn for the following topic distribution. You would have aspect words, you would have sentiment words, and you would have a background words which are just white noise words, like the word food or the word sitting or something like this, which are just white noise. So there are 3 of those. So this aspect would be specific to single restaurant, to single product. This one is carried across all the products, and the background is carried across all the products. And in addition, we will have transition distribution to show us what topic transition. So if you use phrase like, I don't know, delicious cake or wonderful appetizers, you would typically have a sentiment word followed by the aspect word. Okay, so there will be certain patterns on how these colors would appear in a text. So, and as I said, we have several distributions. So we'll have global distributions which are carried across, restaurant-specific distribution, then structure for the individual snippets and the words. Let me just go fast for all of those. So globally, the things which are shared by everybody are background, then the sentiment distribution, where you would have positive or negative bias for your sentiment words, and this is a transition distribution. So it will be just simple HMM, which shows you how you switch from one topic to another. Next, for each restaurant, you would have aspect distribution. And here, in an ideal case, you would say maybe it makes sense to lump together aspect distribution for all the Japanese restaurants and for all Italian restaurants. We didn't do that because there are many restaurants which are modern fusion and kind of thing. It's not really clear with whom to lump them. So we just line separate aspects for each one of these restaurants. Then there is a binomial which tells how likely the certain sentiment for this restaurant will be positive or negative. And there is also probability of each aspect, how likely you're going to talk about it in the review. So those are the three. Then we have a structure of our snippet. So each snippet would be, it will have an, we would assume, and here I'm making a hard-coded assumption, that each snippet would have a single aspect, meaning it will be either about food or about ambience, and it will have a single sentiment. Now here we're making a bit stronger of assumption because you can really easily construct example where the snippet may have two, but in practice it happens rarely, and it's okay to drop some, and finally, we also have this what topic sequence, which shows how the topics change within a snippet. And finally, give it all, we will generate the words. So it turns out that, it's like, as usual, this posterior is intractable, and we're just using standard variational techniques to deal with this issue. To test the system, we again collected this Yelp restaurants. In the same restaurant, we augmented it a bit. And then we did something, there was a bit of manual work here. We seeded a set of positive and negative words that we knew are true for the restaurant domain. We didn't work hard on it, we just sort of looked at the data and decided. So, you would say that this model is unsupervised. It's unsupervised, but it has this particular piece of manual annotation, which is like 70-something words. Did I say something unclear?
Excuse me, maybe I misunderstood something. What do you mean by 7.8 words per snippet?
So the first model that I described just before I came here, in the previous part of the talk, sorry. We extract the sequences, correct? Like the sushi was delicious or something. So on average, the length of the snippet is 7.8 words. Just to give an idea, how big are the chunks that we are operating with.
Thanks.
Because you would see that if it's 7.8 and we assume one sentiment and one aspect, it pretty much happens to be that you have two content words and the rest is garbage. Okay. So there are three different, okay, we created a gold standard, we collected it via Mechanical Turk. Sorry, yes?
Why the model is generated?
Why it is generated?
Because
you.
I think it would be pretty hard to estimate all the parameters.
You will see, like in our case, in order to do it discriminative, in most cases you need to have some annotated data, correct? Now, we decided not to get annotated data because, as I was just saying here, actually for human to sit down and aggregate was hard. Because this was our choice to do it unsupervised, and once we committed ourselves to unsupervised, sort of the natural choice, you can think about it, is a generative model. Now I tell you the story about generative model, and I told you how we estimated it, but it still may not work, and that's why you're going to see the numbers that tell how well does it work. But think about it, that if you want to create your training data, you need to show to somebody, 20 reviews for a restaurant, and ask them by hand to go over the snippets and aggregate them together. And typically we quite successfully can collect this data via Mechanical Turk. It was actually painful, and we had to do all this agreement and combination just because it's hard to remember what you read 3 seconds ago and to keep in memory so much text. Okay, so this is our gold standard. Now, since I told you before that you can just use your favorite clustering, it happened to be that my student Christy Soper loves Cluto clustering, so she used it as a baseline. And we use MARC evaluation technique. So MARC is a competition for information extraction that was popular in the 90s, but people still use the metrics. And there you just look at whenever you have a gold clusters and you have whatever you produce, and the way you evaluate the distance between the two is how many merges and splits you need to do. So there is some standard technique. What we did, okay, there is like some sticky pad, which is how many clusters would you generate per restaurant. Then you can do non-parametric model. We decided here to save ourselves from the pain, and we just decided we're going to generate 10 clusters, both for the system and for the baseline. And I think the reason that we come up with this magic number 10 is we look at what human generated. It was very much close to 10. Okay, so here you can see that we do gain over the baseline. We get another 6-point-something% over the simple clustering. I would let you decide whether it was to go through the pain of building and estimating the model for 6%, but it does work better. You can see the type of mistakes that the model, our model does. So you can see that there is the carrot cake cluster, which talks about how great is this carrot cake. And here the baseline produced to us this cluster which says the carrot cake was delicious, and then the pasta bolognese was rich and robust. So because they both had the word delicious and rich, because of that snippet, they all got clumped together in the baseline. And we looked at the mistakes of the model, which were, as always, very informative. So, like one mistake that the model does very frequently, if you have a word, a phrase which is like the word blackened chicken and chicken enchiladas, which happen to be two different dishes, simple bag of words model put them together because they appear in similar contexts. Or this was particularly embarrassing one, cream cheese and ice cream happened to be clumped together. But again, those are not the very common dishes. If you see like a restaurant which has a lot about ice cream, there are enough ice creams there, you typically separate them. There is also some words which are very rare sentiment words in our corpus. There's just one word, craveable. It definitely didn't recognize it correctly. Sometimes we cannot deal properly with negation, like was not bad. This is the type of mistakes that we are doing. Again, here is a paper and there is a code there. You can try it. Okay, so now I'm going to talk about something else. And I should tell, I don't personally use Twitter, but my students love it dearly. So they wanted to do something on Twitter. And this is a part of the talk about Twitter. So Twitter is interesting and difficult for other reasons than reviews. So what we want to do is to take this stream of tweets and create a table of content. So the idea is there are a lot of events that happen in some city, and you want to have like sort of a gold standard record of everything that's going on, because you assume that if something going on elsewhere or supposed to be elsewhere, somebody will talk about it on Twitter. Like our, let me just show you the output. I brought the output with me. What happened? No. I got confused here. This is an example of output. So you can see the name of the artist and the location where this concert happens. This is automatically extracted output. So our big idea there was to not a big idea, no, big application. A big application there was to supplement like New York calendar of events. So New York, Boston. Boston just doesn't have that many events, but it does have some. In New York, you have this table of content, table of events that is manually generated. And what happens is that many events, which are good, great events, just do not happen to be there because there's some local events or just happen so, some new unknown artist. And the New York table is done by hand. We wanted to have something totally automatic. What I don't show you, and we do that, we also have the whole stream of tweets that is aligned to this particular event. So you can, for instance, measure the sentiment of all the tweets and see how it changes over the time. We'll just go and see what people say about different events. So, and you know, there are obvious challenges. How many of you do use Twitter? I don't use Twitter. See, it's good to be here because, like at MIT, I always feel like a relic and like retirement house kind of person because I don't use it. Good, good. So, at any rate, again, I sort of don't feel it's the right medium of communication, but there are plenty of people who do feel like this. So the challenges are that the messages are very short. They don't contain, you know, individual message may not contain all the fields. You can just say part of it. And the mapping between them is not really clear. If you look at this particular message, like here, the Carnegie Hall is just called Carnegie, and then Craig Ferguson is called Craigie. So there is a lot of this kind of things where you don't really use proper name for the artist and proper name for the venue. You use alternative names. So you would say, how actually I can allot a stream of garbage and produce something of value there? Because, correct? Because each one of them is noisy and bad. But the good thing is you have a lot of it. You have lots of garbage, so you can mine the great things out of it. So here, you can see that many people talk about this event with Craig Ferguson. Some of them may have mentioned the name. Others may have mentioned, you know, other things. So you can try and collect and all these pieces together and use them to drive your extraction mechanism. So what we are going to be doing, I will show you the functionality of the system first. So the first thing that you can do, you can just look at every sentence, correct? At every, not sentence, what are they called, messages. And again, use your favorite sequence model to identify the role of every word. So in this case, it can be artist or venue or whatever, or none. Okay? So this is your prediction. You will do this prediction for each single message. Next thing that you're going to be doing, you're going to be grouping messages that talk about the same events. And finally, you're going to be creating these event records. So you, for instance, you're going to identify these two red pieces together, and then you're going to get Radiohead in Coliseum. Okay, so it's three things. On each one, we identify the roles, we group them together, and then we create the record out of here. So the way that we trained this model is we didn't want to do like a lot of annotation, so we just took a table for a city and the corresponding field of message, not corresponding, so just a stream of messages that we've collected. So in this case, what you don't have, alignment between record and messages is not observed. So you don't know how each individual message is annotated. You don't know which of these messages correspond to which value of the table. You just have two parts of this annotation. Okay? So here it's another example of a messy model. And the reason that it is messy is because you want to talk about different sort of to factorize this whole process into different constraints that you know should be holding. So you would have a part here which looks just at the sequence labeling. You have potential which deals with sequence labeling. You want to make sure that that you have unique records, that you don't extract, that you generate many records which have high overlap, that you sort of combine all the relevant messages into one. And there are some others. Let me just show you very fast how they look like. So this is a sequence labeling. One is just standard conditional random field that looks at the words and based on the local context predict what is a, you know, what is a, what kind of slot does it fulfill. The next one is a term popularity. So here, what you would want to do is to match each of these messages, each token in the message, to the corresponding value in the table. It's another potential. You want to discourage generation of records which look very similar one to another. And finally, you want to make sure that there is a consistency, meaning that you have all values, record values in a single message. You don't want to create a situation where you extract the names, let's say, from one set of language messages and the venues from another set of languages. You're generating artificial events. You want at least sometimes see them together. Okay, and again, it's another variational inference. You can do it. We've done it. And then this is the results, the evaluation of the system. So you have a Twitter data for 3 weekends in New York. What we did, and somebody asked me from Yandex people before the meeting, how did we clean up the Twitter? So we wrote a very simple classifier for discriminating the message, for deciding about the type of the message. And it's a lousy classifier. It gets like 70% accuracy, but it's still okay. You don't have to have a perfect one. As far as it's sort of majority of it is okay. And it's also okay if you have a low recall, because there's so much of it that we can lose. So the resulting data set is 5,800 messages. So this is our training and test split. And as a gold event record, we use this NewYorkCity.com calendar of events. So in this particular days, we had 11 events in training and 31 events in test. And the baseline, the sort of closure to us, which comes from information extraction community, is to do the following. You separately go and you annotate each event. You predict for each, for each document you tweet, you predict the artist and the value. So you do this extraction separately, and then you just do the voting. You say, if I put them all together, I am going to create a record if many of these records are going to be. You have a question, sir?
No. It wasn't related to your talk.
Sorry, I'm just jet lagged. So like talk is, I'm showing places incoherent, so just stop me if I'm incoherent. Let me just rephrase what I've said at any rate. So you do individual extractions, and then whenever you're filling in the records, you're just doing the voting. That's it. It's a very simple thing. You don't need to do anything sophisticated. Just run your CRF, combine the results, and you're done. So this will be CRF voting baseline. Then we have a list baseline, and this is the obvious thing that you can do. Most of the artists that perform in New York City are sort of famous artists, correct? So you can say, I can just go create myself a list of all the artists that appear in the tweet and all the venues, and just say whenever I see the name of the artist and the venue in the tweet, it would create for me a valid record extraction, correct? Sounds like a reasonable thing to do. So as you can see here, in terms of, so this is a precision. So there are 2 versions of our system, the purple and the blue. And you can see they're winning all the baselines. So the difference between the blue is the one that I sort of told you, the purple is the one that I told you about. Now, we did some sort of post-processing. We realized that even though we encourage the model to look at the cases where you have both an artist and the venue at the same message, sometimes it actually makes choices which are not consistent. So we just impose hard constraint. If there is a record that was never the artist and the location never appear together, you just discard it. So you can slightly improve precision. And the evaluation of recall is actually funny. Because, so this is depending how many gold records do you have. You know, you can just decide how much to cut. So you can see that you sort of get reasonable numbers here, and you know, if you allow many records, you get some, 65 of the percentage. Now, when we came back and look at the precision, what we did for precision, let me just tell you, this was not sort of totally automatic thing. What we've done, we looked by hand and seen that, because many times the model predicts pieces which are actually not in the data. That it may predict a concert which was not there. So we had a graduate student go and look at all these mismatches for all the models and say how many times these events actually happened at that time in New York City, and when it's not, and we added it to the gold records. Because the gold records are not really gold. Okay, this is a paper in the code of the system. And let me just conclude and say that there are a lot of interesting and unique challenges for using NLP within social media context. We did see across all of them that use of modeling relation or linguistic properties that you know about, you can get some benefit. And we see that doing it jointly rather than separating it, it typically does improve the prediction accuracy. That's pretty much it, and it's 8 o'clock. Thank you.
My question is about what mechanism do you use for making model selection, tuning number of aspects, number of topics in your models? What methods do you use?
So, for number of aspects. So in this case, we actually have seen that we don't have any principle. In this particular case, we didn't have something very principal. And the reason we've seen that, for instance, for the second model, it's pretty robust. If you give the range, like the number of aspects that we know should be, roughly speaking, 5. We looked at the range from 5 to 20, and we've seen that the difference in prediction accuracy was not very significant, so we just selected a number. And I think in the paper we actually show that it's not very sensitive to this particular, prediction for this particular number. I think that what we've done for some other models and parameters, we just have a development set on which we tune some of these numbers. And again, if you look, there are some parameters which are sort of really not set. If you, in the previous model, when this is how many records do you extract, how many we don't know. We just look at the different thresholds and look at the, how accuracy changes, and then you can decide: do you value more precision, or do you value more recall?
So you're using in-field methods for inference, right? Mm-hmm. And how do you train the model? What method do you use for training? Is it some variation on the maximum likelihood?
Yeah, so we actually do train the pieces of the model on some sort of maximum likelihood pieces and parts, like for the last model.
I see. And haven't you tried, SSVM, for example?
So what?
Structural SVM.
So no, we didn't try it for this one. No.
This is an interesting question. Maybe it will work better. According to recent papers, SSVM works better if the probabilistic model doesn't respond to the ground truth.
If the probabilistic model doesn't respond to the ground truth, we didn't try it. It could be something to try.
No, that was just a remark. Thank you.
I just get one question. So I didn't really get. So you're trying to predict future events, or trying to recognize that this event happened in certain places? So
we're not trying to predict future events.
Right. So
what we're trying to do is to. We're trying to. So what do you mean future events? We're not trying to predict. We have the stream of events when we're training. We have the stream of events and the table. During the testing time, you just have the stream of the future that you haven't seen during training, and you're trying to build a table of those events.
Yeah, but it's like mostly people tweeting about the events which are happening now, or you're also you can sort of predict events.
So we don't care if this event happened in the past or if this event is. We don't discriminate. So in this case, what I showed you now, we don't do the time, because time is actually requires something separate to do the modeling. So we can extract the time. So if you have the time, you can predict whether it happened or it will be happening.
I mean, for the task of building an agenda, it would be more interesting to predict events, right? So what you mentioned in the beginning, that you want to have an automatic list of upcoming events.
So if you have the timestamp, you can actually see, is it an upcoming event or is it a past event? Because you can associate not the time for the tweet message, but the predicted time of the event. It's just a paper that we published, that's why I stick to it. We talked about the tool, but you can use it to extract the time. It's slightly different. Okay. Thank you very much.